we got a little bit stuck on the example 5.2, where we tried a transformation in the x variable. And I have that fixed up now so I can show you a little bit better how that works. The author did make a mistake on that one.
There's a newer edition now.
4th edition now?
There is.
Okay, I don't know if it still has the same mistake. Okay, you check that. So it's a minor point, kind of, but I thought if we're going to go ahead and do iterations, we might as well do it right. So I'll refer to pages 191 through 193 in the text. And I'll go through this just a little bit more. What we were doing and try to do in example 5.2, this is transformations. In the x variable. Okay. Example 5.2. What we're going to do here is we're going to model EY is equal to beta 0 plus beta 1 x to the alpha. Okay, so it's a nonlinear model because the third parameter alpha is not in a linear place. Okay, and there's no way to transform this to a linear model. So what do? What you're going to do is you're going to think of this as a function of 3 variables, beta 0, beta 1, and alpha, for x fixed. Okay, so what would you do if you did a Taylor series expansion? What you'd do would say this is approximately equal to beta 0. I'm going to take some initial guesses, and I'm going to call those with a super 0, plus beta 1 super 0 plus x to the alpha sub 0. I can put that in a sub 0 place, okay, because I don't have another index already. So this is the value at some. So I'm thinking this is a function of these 3 parameters for x fixed. Okay, x is just fixed now. Now plus, what you would do is that you would put in the gradient of this function of beta 0, beta 1, alpha. Okay. Which would be, if I call this a function of f of beta 0, beta 1, and alpha, okay, then this is the function at some initial values, okay, plus then I would put the gradient of f at beta 0, 0, beta 1, 0, alpha 0, times the vector, or dot the vector, beta 0 minus beta 0, 0, beta 1 minus beta 1, 0, alpha 1, or alpha minus alpha 0, like that. Okay? So beta 0 is the actual value of the parameter, and this is an initial guess. Beta 0 super 0, beta sub 1 super 0 is an initial guess. Alpha 0 is an initial guess. And our initial guesses are going to be from the simple linear regression. So our initial guesses are going to be beta 0, 0 equals beta 0 hat, beta 1, 0 equals beta 1 hat, and alpha 0 is equal to 1, where a beta 0 hat and beta 1 hat, beta 0 hat and beta 1 hat are the least squares estimate for simple linear regression. So that's what we're actually going to take as our initial guesses, and alpha 0 equal to 1. And then I want to update that. Let's see, what happens then? This is equal then to, the way we did it, just the author wasn't maybe real clear about this, but I'm going to make it real clear. this is times x to the alpha, not plus. Sorry about that. Okay? Times x to the alpha naught plus, what is the gradient in these three variables? The derivative of f with respect to beta 0 is simply 1. Okay? So you simply get 1. The derivative of this function with respect to beta 1 is x to the alpha. And of course I'm going to plug it in at alpha naught. And then the derivative with respect to alpha, we said, was beta 1 x, excuse me, log x, and then x to the alpha. And I'm going to put it in now, alpha naught for alpha. What I'm using off on the side here is the derivative with respect to alpha of x to the alpha is log x, x to the alpha. That's going to happen over and over again. Okay? And so I'm going to use that off on the side. So I'm just going to make this really precise, exactly what I'm doing. Dot this vector, beta 0 minus beta 0 super 0, beta 1 minus beta 1 super 0, alpha minus alpha 0. Now put all this stuff together. What do you get? You get 1 times this beta 0 minus beta 0, 0. What happens is the beta 0, 0's cancel. Alright? So you just get beta 0 without the initial guess. Also, what happens here, you get the x to the alpha naught times beta 1 minus beta 1 sub 0, and that's plus, and then cancel the beta 1 super 0 x to the alpha naught. That's why the author didn't talk much about this, because you actually get these things canceling. You just get what you'd expect here. All right, you just get the beta 0 plus beta sub 1 x to the alpha naught. All the beta naught super naughts gone away, and then plus the last term, though, there is still a beta 1 super naught there. Plus alpha minus alpha naught times beta 1 super naught log x, x to the alpha naught. Okay. So that's what your regression function looks like as a linear approximation. In a linear approximation. Now it's linear in the parameters, Okay, where now I have a third parameter, which I'm calling gamma. I call this gamma, I call this beta 0, and I call this beta 1. Okay? So it's linear in those three parameters. Alpha naught is just a fixed number, it's 1. Okay? Beta 1 super naught is also a fixed number, but it's defining as gamma. Okay? So now what I do is regression on these three variables, and what I get then is that I get, so now you calculate regression coefficients, least squares estimates for regression of y on x to the alpha naught and log x, x to the alpha naught. Okay? Now, and I'll get, and I'll estimate then that alpha 1 minus alpha naught times beta 1 super naught, okay, which is my original estimate of the slope, just a straight line, okay, equal to gamma hat, okay, on this situation, okay, and I'll therefore get that alpha 1 is equal to alpha naught plus gamma hat over beta 1 naught, okay. And that's it. Okay? Now this was true no matter, this is independent of what I started with, whether I started with alpha naught equal to 1 or alpha naught equal to alpha 1. This is just the iteration. So what do? Now we're now beta 1 super 0. Now what beta 1 super 0 though is at least for simulated regression of y on x to the alpha naught. Okay? So that's where the beta 0 hat and beta 1 hat are. That finishes what beta 1 super 0 is in terms of this alpha naught. So I give myself an alpha naught. I get myself a beta 1 super 0. Okay? by regression of y on x to the alpha naught. Okay? And then I just go through this process. Now I got an alpha 1, I replace alpha naught by alpha 1, do it all again. It's exactly the same, okay, with alpha. So now there's no log x prime or whatever. He called this x to the alpha naught x prime. Okay, but then he put a log of x prime in here. Well, that changes things because log of x prime will then be another factor of alpha naught, which is about minus 0.9 or minus 1. So that changed the sign of the iteration. Okay, and you can see that I actually showed this how it was corrected. There's a mistake, so he shouldn't put the x prime on under the log. Let me just grab this worksheet and get the correction. What is it? It is called Example 5.2. This is it, I think. Yes, that's it. Open. I've got it changed now, corrected, and on the website. Let's view normal. Okay, and let's bring it down. Okay, so any comments about this? This is the iteration then. So then I just go back here and I replace alpha naught by alpha 1. Okay, and do the loop again. All right. Is everybody following that?
You don't change your beta estimators?
I do. Beta, yeah, this alpha naught then gives me to this, okay, update this, okay, when I replace, because I'm doing really linear regression of y on x, so it's simple linear regression, but y on, we could call it x prime if you want, okay, here. But there is an x prime, but I don't put the log, when I take the derivative with respect to alpha. You take the picture off for a second while we finish discussing this. When I take the derivative with respect to that's the only place I need the x prime. Okay. Then when I take the derivative with respect to with respect to alpha of x to the alpha, I'm still getting just this log x coming down. Okay, there's no log of x prime. Okay, it's a slight technicality, but it made a difference as we saw at the end of the hour last time. Okay, so here's the way we actually did the windmill example. Okay, we had velocity of the wind. Okay, I need a picture. Okay, so we had velocity of the wind. Okay, that's x. I'll just go ahead and highlight these two. All right, so then we have x, and those are the velocities. Then we had y, which is the DC output of the windmill. Okay. And now I'm preparing to do the first iteration by putting this x log x, because alpha naught is 1. Okay, so this is really x to the alpha naught log x. All right. I just stuck those in there. Okay. First, though, I did simple linear regression to make sure that I need to do any transformation at all. And we noticed that if I do the simple linear regression and I compute the residuals, then I get this frowning face pattern, okay, of the residuals, which indicates inadequacy of the model. Okay. I think then, I'm not sure if I did any normal probability plots or what have you. Okay. Then, okay, now I'm going to follow this process where now I'm going to do the simple linear regression, or the multiple regression of y on x and x to the alpha naught log x. All right, I can put here alpha naught equals 1. Okay, and so this is x log x equals really x to the alpha naught log x. Okay, so that's, oops, I did too many parentheses. Okay, so that's what I'm doing there. Okay, so then I do the simple linear regression and I get my gamma is negative 4626. This is just some beta 1 hat, but it's not the beta sub 1 super 0 that I was talking about. Beta 1 super 0 is, well, here it is right here. This is my beta 1 super 0. Okay? That's my initial slope that I plug into this formula for, well, now that I can't read it on the board, my formula for alpha 1, which is alpha naught plus gamma hat over beta sub 1 super 0. That's my beta sub 1 super 0. So that's what I've done over here. I've got alpha sub 0 plus gamma hat old beta, I call it old beta 1 hat because there's too many superscripts and so on. Okay? Because 1 plus negative 4626, which is this right here, that was my gamma hat. Alright? Divided by the 24, did I do it right? 24115, that's right. Okay? This one was 24115, that was my old beta 1 hat. Okay? 24115, and then I get the negative 0.91. Okay, for my alpha 1 is negative 0.91. Now, I'm going to do what I say is the right thing to do. Okay? And that is, as you can see from the math, it looks okay. And that is to go ahead and put x, as it was before, x prime now is x to the negative 0.91. There's no difference from what the author did at this point. Okay? Bold that. Okay? So you can see that. X prime is that. Go ahead and do the simple linear regression there. And I obtained my beta sub 1, my second iterate, my beta sub 1, super 1 you could call it now. Alright? It's my next value of the slope. Negative 6.6. So things have changed quite a bit. Okay. It's a different variable. Okay. So negative 6. So this is my beta sub 1 super 0. My alpha sub 0 is now negative 9.1. I'm just going to use the same terms, right? And I'll just do the whole thing again. Alpha sub 0 is now negative 0.91. Beta sub 1 super 0 is now negative 6.65. Okay. All right. So what am I going to do? Now I have to do the multiple regression on x prime, and log x times x prime. Okay? X prime was x to the negative 0.91. Now it's log x times x prime. Okay? And I obtained then the simple linear regression there, and I get my gamma hat now is negative 0.49. That hasn't changed that much. It was negative 0.46 before. Okay? And what do I get? Alpha 2 now is alpha 1 plus gamma. Well, I guess I did change the indices. Alpha 2 is alpha 1 plus gamma hat over the old beta 1 hat, which is now negative 0.835. As I indicated, it was going the other way than the authors. All right? Okay. Now if I do it again, I think I even did it again. Let's see, did I do it again? I want a regressed on, yes. Let's see, did I do the simple linear regression on just negative 0.835? That's what I'm looking for. Here it is, no. There was the multiple regression, and things didn't change very much. Wait a second. Oh yeah, the coefficient became 0 essentially on the gamma. That means I'm done. When I did it again. Right there. I said, okay, that's enough. Alright, so it really did converge. Alright, alpha was constant now, because alpha minus alpha naught times beta sub 1 super 0 was the gamma. Beta sub 1 super 0 was still negative 6.5. In fact, here you can see the negative 6.5 is the coefficient, so those match now. If I had done simple linear regression. Okay, so it's as if I had done simple linear regression or multiple regression, wouldn't have made any difference. Okay, because now the gamma is 0. All right, so that's showing you that this works. Okay. Now, because of it, if the formulas hadn't been right, it would have continued to change and so on, and flip around and so on. So anyway, what I did then was I actually go ahead and going back here, I actually took the negative 0.835. Let's see, what is this? This is simple linear regression. This is simple linear regression. I didn't say so, but it's clear from the notation maybe. I just have two variables. Let's see. X double prime is x to the negative 0.835. Okay? So this is simple linear regression, or linear regression of y on x double prime. Okay? Period. Okay? No second variable. All right? So what did I get? I got a mean square of 0.00846. Here, MS res is 0.00847 versus 0.00886 for the Alder's reciprocal transformation. So I'm saying I got a better result. Okay? So it really is a closer fit. All right, here are the two pictures of the fit. In other words, of course I can't, yeah, that's it. I'm trying to get the best fit. All right?
So for your final beta estimators, do you use the simple model, or do you use the next iteration?
Well, no, I could do the next iteration. It doesn't matter because they're the same. They should have converged. I got negative 0.647, and I got over here negative 665. Okay. One more iteration if you really wanted to the next digit, but okay. I just wanted to point out that we're just about done. Okay? I didn't want to have to go through any more work. Okay, because it's already long enough. Okay, go away. Now, that's going to freeze the computer that I canceled the office assistant, right? It did. No. Let's see. I put the residual plot for regression of y on x double prime. I just showed that as close enough. Okay, it converged almost in one step, or two steps. Then here's the pictures. I tried to blow it up a bit. One of them, series 1 was, as you can see here, is the answers. It was the reciprocal transformation. It was the Alder's reciprocal transformation, and this is the one with, because that's the x to the negative 1. All right? And this is the x to the negative 0.835 is the red line. Okay? So it's a little bit different. Okay? I could blow it up even more, but it's fitting just a little bit better. Okay? So it's hard to tell. You know, if you just look at the residuals or something like that. Okay. Anyway, that was that business. So there's your iteration. Okay. Now, we need to talk a little bit more about weighted least squares, because that's what we're going to do next. Finish that up out of Chapter 5. I did start weighted least squares, but now I'll just start it again. Okay. This was kind of a small example, but it still gave you the iterative process kind of a picture. I think it was a kind of a cute example, actually. But I guess beware of people that have a self-fulfilling prophecy there. Okay, the negative 1 exponent, which is too good to be true. Okay, why would that be the case? You know. So, it was curious that it came out that way, though. Let's see. With the mistake. Let's see that. We had started discussing, and of course the notes, these notes 7 on page 3 are kind of messed up, actually, because of this correction. So you may have to fix that up. Okay, I think I wrote one of the formulas for alpha 1 wrong, and I put in these super zeros to make it clearer what was going on. So you might want to fix that note 7, page 3. I'm going to continue on for note 7, bottom of page 3, weighted least squares, and to the top. Okay, so what we're going to do is assume that our regression function is linear, all right. Y equals x beta. All right. I mean, linear in whatever x variables I have. The x variables themselves might be e to the x. Okay. That's all right, as long as I have a linear relationship with respect to the betas. So I'm going to assume this, my usual assumption, y equals x beta plus epsilon, but now I'm going to assume that the variance covariance matrix of the epsilon vector, which was an n by 1, this was n by p, beta was p by 1. I'm going to assume the variance covariance of epsilon now is sigma squared times a diagonal matrix where the diagonals are weights. 1 over w1 are reciprocals of weights. It's a certain, where the wi are greater than 0. Okay? This is a certain parameterization. So the variances are proportional to the reciprocals of the w's. There's some column of w's that I'm going to introduce. Okay? I mentioned last time that we could actually study the Poisson data in this way, but I'm going to go ahead with the general business. What I'm going to do then is I'm going to introduce the following thing. I'm going to take z equals a certain. I'm not going to name this matrix. I'm just going to put square root of w1. I'm going to put a diagonal matrix, square root of w1 through square root of wn. And I'm going to take that times y. And that's going to be a new column of z. So all I'm doing is taking the y's and turning them to z's by multiplication by a certain column, term-wise. So I think what I'm going to do is I'm going to have my original x's. Let's say in a simple linear regression model, I'll have my x, I'll have my y column, and then I'm going to have a w column. Somehow, where is it going to come from? Whatever arguments I have for how the variance covariance of this thing should look. In the Poisson data, it would be the variances were proportional to the mean. Okay, so then I would put 1 over the mean and do a kind of an iterative procedure, right? Readjust the weights, because then the mean would change as I did the process. So I did the weighted squares. Okay, so I have to come up with a w somehow. All right, and then I would just put the square root of w, and then I would just put the square root of w times x, and the square root of w. Well, I talked about making the square root of w times y. Okay, so let's see. I'll do that, and I'll also define a new capital U matrix n by p to be simply the square root of w1 down to wn, like this, times the x matrix. And so actually what that is right here, because the first column of the x matrix is 1s. So this is the square root of w times 1. The first column of u will be simply the square root of w1. So this is going to come out like this. Square root of w n times 1 times 1 times 1 if x is the x matrix. The second column of u will be the square root of w1 times x 1 1 square root of w2 times x 2 1 square root of wn times x n 1 if x1 is the first regressor. Here I've only got one regressor in this little example. Okay, and then I'd have the square root of wn, square root of w1 times x1 k square root of w2 times x2k down to square root of wn times x nk. But in principle, probably the best way to think about it is constructing these columns in your Excel worksheet. Okay. So I'll do that. And then I have formally I'll have also delta the error vector is going to be formally equal to then also the square root of W1 down to the square root of Wn, just a diagonal matrix times the epsilon vector. Okay? Alright, formally that way. So then what I have is that y equals x beta plus epsilon is true if and only if I'm going to multiply both sides by this square root of W diagonal matrix, if and only if z is equal to u beta plus delta. Where now the variance-covariance matrix of delta is simply, let's see, I would have this matrix, I'll just write it down, square root of W1, square root of Wn, times the variance-covariance matrix of epsilon, I'll write it like this, times the square root of W1 down to square root of Wn. Transpose, of course there's not anything to transpose, we've got a diagonal matrix, and then this simply comes out to be, because it's got square root of W's twice, remember the handy-dandy formula for the covariance of a matrix times a vector? It was covariance of a, what did I put in here? Just about any vector here. A m by n times some vector v, but that's the random vector n by 1. Okay, that came out to be, that's the handy-dandy formula, the variance-covariance matrix of v times a prime. That was the handy-dandy formula that we've used before. Okay? So this is the random vector. Okay? And so I got this, and since covariance of epsilon was assumed to be of the reciprocals of W's on a diagonal, it's just multiplication of diagonal matrices. It's trivial. Then you simply get sigma squared I. Okay? So now this equal variances assumption holds. And the betas are exactly as they were before. Okay. So, how could we apply this? Okay. Let's see an example. Which one do I want to do? See, what do they have in the book? I can't remember. Because it's been a day or two since they did this. Okay. Where did they do the weighted, these squares? Aha. Transformation of generalized model, generalized weighted least squares, there they are. Oh, restaurant fruit sales. I'm going to do something in between. I'm going to fill in a little bit more on this because he jumps to restaurant food sales data. I'm going to do, I guess I'll do an exercise out of the text, 512 first. And try to show an example for it. And then to show how this works. That's the simplest example. Problem 512. Let's see if I have that here. Yes. Problem 512, page 5 of these notes 7. Okay. So let's do a few weighted least squares problems and finish this thing off. Okay, maybe I'll leave that up there. So, exercise 512. States that suppose I have the simple linear regression model, just y equals beta 0 plus beta 1x plus epsilon, but now we're assuming that epsilon has variance proportional to the square of x. So the standard deviation of the response is going up linearly. And I have this one text, regression analysis by example. There's a text by Chatterjee and Price. It doesn't have any exercises in it. It's just a how-to kind of read a book on how to do regression after you've already had a regression course, probably, or why you're having a regression course. It's a nice little book. I think I mentioned it. I think on one of these web site documents, on one of the Excel documents, on the supervisor's data. There's some other data I'm going to pull from that book. He said in industrial examples, it's not that uncommon that the standard deviation would grow linearly. Okay? In that example that we're going to see, there were you had various companies, you had various number of workers, and the larger the company, the more workers, and you had the number of supervisors for those workers. Okay? Well, of course, you'd expect that to grow linearly. Okay? But it turns out that the variability in the number of supervisors also was growing. Okay? The larger the company, the more variability there was, across companies and so on. As to how many supervisors they actually kept. All right. So there was an example where the variance is growing as the square of the regressor, or approximately as the square. Let's just pretend it's exactly. Okay? So let's take this yi equals beta 0 plus beta 1 xi plus epsilon I. Assume this, where the variance of yi is equal to sigma squared times xi squared. Let's say exactly something, some constant proportionality times xi squared. The actual value of sigma squared is not important.
Variance of EI.
I'm sorry. Same thing. Variance of yi equals variance of EI. Because remember, if you change something by the mean is the constant, or the x's are fixed. So, all right. The variability of the y. It's just the height of the y is raised up, okay? But the variability is the same as the variability of the epsilon, okay? Now, if we divide through by xi, we'll see what happens. So that means that wi, 1 over wi, equals xi squared. Okay, so that means that wi, right? Or it's sigma squared xi squared, but that's just the way I'm going to take my weights. Yeah, that's right. 1 over wi is xi squared. So wi equals 1 over xi, okay? And the square root of 1 over xi squared, and the square root of wi equals 1 over xi. So I got that right. I think I do. All right? We'll just go this direction, even though it's if and only if all the way. Okay, we'll assume that xi is positive. Okay. So that's what I'm going to take. I get so then I'm going to take my z equals the square root of wi. So that means my z, if I call this my z, equals the square root of wi. Zi equals the square root of wi. That becomes yi over xi. Okay. My square root of wx becomes xi over xi equals 1. Okay. My square root of w times 1 becomes simply xi. This would be 1 over xi. Okay, times 1. See if I got that right. Yeah. So those are my variables now. It's 1 over x now equals, okay, and it's 1, and it's z. Okay? Am I doing this too fast? I'm just saying what I would do what I'm going to do to find my estimates of beta 0 hat and beta 1 hat. I'm going to make a column of the square root of w. I'm going to make a column of the square root of wxi. Those are going to be my u0 and u1, if you like. All right? My u0 and my u1. And I'm going to make a column of responses, z. Okay? So there's a column. The first column of this U matrix is what I call the variable U0, right? Corresponding to the beta 0, right? And then the second column I'd call U1, corresponding to the parameter beta 1. Well, now, what is it? It's U0 is simply 1 over the ith element of U0, or the column U0 is 1 over xi. The ith element of the column U1 is 1. Okay, that's like kind of strange, because now the intercept, now I have an intercept model, right? So what I have is that y equals beta 0 plus beta 1 xi plus error if and only if z equals beta 0 1 over xi plus beta 1 times 1 plus delta I. So now the roles of beta 0 and beta 1 are interchanged. If I regress z equals y over xi on, or z equals yi over xi on 1 over xi. So what I'm going to do is I'm just simply going to get, what I'll get is I'll do simple linear regression of z on 1 over x, okay, obtain estimates, intercept, and then 1 over x, right, in my Excel sheet, right? And this is under coefficients, right? This is what Excel comes out with, doesn't it? Comes out like that? Yeah, I believe so. That's what they label after the ANOVA table, they call it coefficients. Well, they don't actually label it anything. That's the first column is labeled coefficients, and then they put standard error and all that stuff. Okay. This is blah, blah, blah. Okay. And so I'm going to get the intercept. So this is, whatever this is actually going to be my estimate of beta 1. Okay? Because the intercept here is the beta 1. So it's like the roles are switched. Okay? Does everybody see that? Let's see how it works out. So this is going to be my estimate of beta 1. Okay, and this is going to be my estimate in my original model of beta 0. Remember, the betas are the same as they were. Okay? But because of the way this is working out, just the way it's working out, okay, then the estimate of the slope of the z equation, okay, is actually my estimate of beta 0 in the original equation. Or if I don't do it that way, I mean if I did it formally, just made the first column the 1 over x's and the second column the 1 over the 1's, okay, and did it by hand, my first entry would be beta 0 hat still, okay? But I'm switching the columns when I do it with Excel. I'm switching the columns of u. So I'm regressing on 1 over xi, and so because the intercept is already there, automatic in Excel, right? So I'm switching the columns. That's why they're coming out in reversed order when I play with Excel. Does everybody follow me what I'm saying? Switching the columns of u. Okay. So let's do that. Let's just go ahead and find this data. I don't think I need this worksheet anymore. Wind velocity, we're done with u. Okay. And let's find out example supervisors. Where are you? Did I bring them down? Unequal variances, is this the one? Yes, that's it. Okay. So you're not familiar with this data, so let's have a little look at it, gander at it first. Supervisor, transformation to remove heteroscedasticity. That's unequal variances. Okay. That's the statistical term. Maybe you should all know that word anyway. Equal variance is homoscedasticity. Unequal variance is heteroscedasticity. Okay? The long word for unequal, well, I guess it's virtuous that it's one word instead of two words. Unequal variances. How many syllables is unequal variances? That's quite a few, too. This is heteroscedasticity. I think it may be that this wins is fewer syllables. Unequal, this 3. Variances. If you call that, that's variances. That's 4. So that's 7. Hetero is 3. Ski, that's a tie. Okay. Okay. Whatever. Here's the this number is supervised. Is this 8? Ski, test, 7. 1, 2, 3, 4, 5, 6, 7, 8. Alright. Alright, anyway, it's a joke. Okay, let's go on. I can't count. Number of supervised, and this is number of supervisors. Okay? Okay. What did I see? Let's see the original data if I can. Here it is over here. Here's fitted line for equation. Original variables based on coefficients derived from... Oh, that's a different thing. But that's the scatter plot of the data anyway. See, where's the original stuff? I don't know if I made the original stuff. Okay. Maybe it's down here. No? Oh, I know. That's the summary page. No wonder. Simple linear regression. Okay. Here's the number of supervised workers. That's not a W, that's a workers. Okay? And the number of supervisors. Okay, so here's a fitted line plot for the original supervisor data. Okay? You can see that the variability seems to be increasing about that line, in the vertical direction. Okay. Here's the residuals for that fit. Okay? So it has kind of the funnel shape, plus a little bit of curvature. Okay? So what we're going to do is we're going to go ahead and do this weighted least squares where we're going to make this assumption, this industrial example, that the standard deviation is growing linearly. Okay. So let's see, what else was there on this page? Oh, there was a bunch of stuff. HIIs, I did all that stuff too. Okay, weighted least squares. Regress y prime and w prime. I'm calling them y prime and w prime. Well, let's see. Let's go over here. I don't know why I did that, but anyway. Instead of calling them z and u, I call them y prime and x prime in this worksheet. Sorry about that. So here's the weight, 1 over x squared. The square root of w is therefore 1 over x. Okay, does that make sense? 1 over 294 is 0.0034. That looks right. 1 over 1,000 is 0.001. Okay, so this looks okay. For my w, square root of w is 1 over x. Put it this way, so everybody can read it. Okay? And then x prime equals the square root of w times x. It is in fact just 1. Okay? Instead of calling it u, I'm calling it x prime. Putting primes. Instead of calling z and u, I'm calling it y prime and x prime. And instead of calling it the square root of w, I'm calling it w prime. All right. Okay. I don't know why I did that. But basically what I'm going to do now is do simple linear regression of y prime on w prime. Maybe this notation is not so bad. Okay? I'm not on y prime on x prime, but simple integration of y prime on w prime. We get y prime and w prime with intercept. And that's going to give me the other coefficient that I want. Alright? Sometimes you have to do these weighted least squares without intercept. But since I'm only putting it in one regressor, I have to do it with intercept. If I put in 2 regressors, x prime and w prime, then it would come out, and with no intercept, then it would come out in the right order, right, for the, okay. Excuse me, that I would put w prime and x prime. This would be the first regressor, w prime would be the first regressor, and x prime would be the second regressor in what I had before. Okay, corresponding to the beta, x prime corresponds to the beta 1 coefficient, w prime corresponds to the beta 0 coefficient. It turns out, the way I had done it. So, then I go ahead and I get it. Here's the intercept then, is the 0.1. The intercept of regressing y prime and w prime, again, this automatic method is 0.120. So that's my beta 1 hat. This is my beta 0 hat. Let's just see. Let's compare it with my beta 1 hat from simple linear regression. There's a beta 1 hat of 0.1209. What's my beta 1 hat from simple linear regression? It was 0.105. Okay, so it's a little bit bigger. And what about the standard error? 0.0113 versus here 0.008999. Smaller standard error. Okay, it changed it. Okay, but it has a smaller standard error. Okay, and here's my beta. Here's my beta 0 hat. Over here, that was 14 versus what? 3.8. It's quite a bit different. Okay. Standard error was 4.5 here. That's kind of big. Well, it's not very significant. It was also a big standard error here, which wasn't very significant either. Okay. But it didn't do much there, but it got the slope a lot better. Okay. Okay, so what did I do now? I'm playing a little bit with the residuals. You can get the residuals from this, okay, and see how they are. The residuals from the, now I have the equal variances assumption, the residuals should behave well, okay. So what I've done is I've simply taken the residuals for the transform supervisor data, okay, y prime, w prime, okay, so I'm just taking the residual output from Excel and plotted them, okay, versus the regressor, all right. And they look okay, not super great. You didn't take that curvature out that much, but you got the funnel gone, all right. And there's the fitted line plot, okay. And I don't know, did I have any more summaries? Let's see, I had a little bit something here. Let's see if I got it in the summary page. Prediction equation for the Newell coefficients was here. I called it y tilde is this. That's my weighted least squares line. Okay. Now, since it's a straight line fit to the data, if I actually take that as my prediction, y minus y tilde, and square the errors, I have to get a residual sum of squares which is bigger than my original residual sum of squares for simple linear regression, because simple linear regression gives you the smallest possible residual sum of squares for a linear fit, right? That's the theory of least squares. So if I actually take y minus y tilde and take the sum of squares, which I do here, sum of squares y minus y tilde, I get 12745. Okay, versus what did I get for the error sum of squares, or SS res, in simple linear regression? Let's see how that is. 12745 versus in simple linear regression, I got 11804. Okay, so I am getting a higher MS res 472. But let's see, the R square was 0.77 versus in the summary I had R squared is 0.76. Okay, over 77, 78. So it's not that big of a difference. Okay, SYY is the same, of course, in both models. Okay, total sum of squares. So, okay. So what you're getting is estimates that have a smaller variability. They're more, this is a straight line fit. Okay. Yeah.
I noticed on the simple linear regression sheet you had a column for your HIIs.
Yeah, how did I get that?
Was there an easy way to do that? Or were you
No.
just picking them off and like cut?
I think I did it using Maple. See, I don't have a formula. Oh, I did in simple linear regression. I have a formula for it that the graduate students have to supply.
Oh yeah, that's true. That's on the exam.
Yeah, there's a formula for it in simple linear regression.
Okay.
But some of the other worksheets, I don't have formulas for it. Okay, you might be able to derive a formula in the 3x3 case. Here the covariance matrix is 2x2. Right? The variance covariance matrix of the x prime x is 2x2. If there were just two regressors, you might be able to come up with a formula for HII in that case. That would be a good extra credit problem. But to find a formula in general seems to be hopeless. Otherwise, they would have reported it somewhere, I would have thought. Okay.
I've got a question on the Microsoft board for how to get a diagonal matrix.
You do?
And there was an answer, but I don't understand the answers.
Oh, you do? Maybe we could go ahead and look at that at the break or something. You did get an answer. Who did you get the answer from?
I don't know. Just some guy.
Somebody on the internet.
Somebody else said, yeah, that works. So.
Wow, you actually went out there and found something. That's great. The world responds.
Yeah.
Nice. All right, well, we'll discuss it at the break then. Okay, any comments about this? That's the method. I didn't have to reweight or do anything like that because we assumed our weights were good. Okay, so there was no iterative process here. All right. Comments or questions? All right. All right, let's do another weighted case. Let's see, do I have one more? Oh yeah, the restaurant food sales data. That's the one in your text. Okay. If we do have a method of estimating the variance of y given x, that is the variance of the epsilon, then we can apply weighted least squares like this. So if we have a way we'll assume that the errors are we've assumed the errors are uncorrelated, but if we have a way to estimate the variance of y given xi, okay, equals sigma squared sub xi, all right, or sigma squared I. You could put lots of notations. Some people will call it sigma squared sub y too, because y depends on I. All right. Then we can apply weighted least squares, WLS is what we call it, with the square root of WI equals the standard deviation, sigma sub xi. Okay? Didn't I do it that way? Sorry, 1 over the sigma of xi. Okay, I have to take the reciprocal. That's the way I had it before. Okay. Okay. So this is illustrated in example 5.5, restaurant food sales data. In this example, some nearly repeated measures of the response are available. Okay, so they also have a method at the end of chapter 4, which I skipped, about how to do lack of fit when you don't have repeated observations, but when you have nearby x values. It's sort of a clustering method. I'm not going to discuss it. You just need to know it exists, okay, if you get savvy and do further statistical work, okay? What I want to do here is an example where a slightly different thing goes on. There are repeated measures almost again, but he's sort of done it by hand. So let's have a look at this one, restaurant food sales data. Okay, so let's have a look at the restaurant food sales data. Let's see, what page is it in your book? 197. Okay. And 198 is where they actually show the picture of the data. What they have is they have advertising expenses seem to be, here they've got a sort of a natural situation where either your advertising expense is, which is your independent or regressive variable, is either kind of at the certain levels, like the $3,000 level, the $5,000 level, the $6,000 level, the $9,000 level, the $11,000 and $12,000 level, the $14,000 level, the $15,000 level, the $17,000 or so, 18 and 19. So they sort of have levels to how much advertising you have. He needs enough levels to get enough estimates of the variance to do something. Okay? So let's see. Here you have, I don't have anything yet, that's too far away. Okay. Food sales data. Now, I didn't show everything that's shown on the picture on page 198. I said the advertising expense, and I think the author, for example, suggested that these three levels were equivalent. Get it? Come, I can't format those cells. Anyway, I can highlight those cells just there. Those three X values were equivalent. And then what he had is he had the income from those. And then I take these corresponding three Y values. Okay? Now if I take the sample standard deviation of those three Y values, you get an estimate of the variance. At level X is 3,000 roughly. Okay? So what is it? Let's insert a column here. Is that going to hurt anything down here? Not much. I can always fix it later, I think. Maybe I better not. It'll mess things up. Okay, so let's take this. Let's just go ahead and figure out what he's talking about. Let's take the standard. Let's take the samples variance of those three. Okay, equals variance of these three numbers in the Y variables. Okay, what do I get? I get 26,000. Well, let's make it a bigger, longer, wider column. Okay, it's supposed to be 26,794,620. Okay, that looks about right. Okay, that's the variance of income for that amount of advertising. Yes, the variance. It's not the standard deviation. I take the square root of that. That's why it's so big. Okay, it's 26 million instead of 1,000 or 1.5 thousand or something like that. Okay. Is everybody clear with that? Okay, your income was 8,000, your standard deviation is about 1.6 thousand. Roughly. If you take the square root of that. Okay? And then I go on to the next, let's see, the 5,000s were, they were a little bracket. As long as there's two observations there. There were two advertising expenses of 5,000, so I take the standard deviation of those. Go ahead and do that. Equals... Again, I'm just taking the variance here because I'm working with the variance parameter. Let's see, of these two Y values right here. Oops, wrong thing. No, that's right. Okay, and I get the number which is 30 million this time. Okay, in variance, $30 million squared. Okay, because the units of variance are square units, etc. All right, so then he's established somewhat artificially you might say, these various levels in the X, various strata of advertising costs. We call those strata. All right, and you can either make them. Here it was easy to make them up. Okay, and so he's just getting a bunch of SY squares. Now, where did he get those? I mean, what did he do with those then? Okay, well, he has to have some kind of dependence of X on those S squareds, because I want to have my W depend on X in some sense. Okay, my W my square root of W, which is 1 over the standard deviation, all right, at x. So I need to estimate what the standard deviation at x is. Okay. Well, let's go ahead and I could just put my weights in straight up as these. This is the standard deviation is, one of the standard deviation is 1 over 1.6 thousand for these first three cases, then 1 over something else for these next cases. But instead, he does a linear regression. Okay? That's what he's done in the text. So I'm just going to follow what he did. Regress. Okay, what did he do? Where did he get his formula for his W's? Oh, I know. Here it is. W. Okay, from the text on top of page 199, W is 1 over the standard deviation, and what is the? W is 1 over the variance. And what's the variance of yi? Okay? The variance is given by a simple, what we can do is take these numbers here, these 8 or so numbers. How many are there? 1, 2, 3, 4, 5, 6, 7. There are 7 strata. You take the 7 numbers and do a simple linear regression of those variances on x, and you get this formula here. Negative 73, 762, 16 plus 7820 times x. That's on the bottom. Well, that's the top of page 199. Top of page 199, he's got that formula. So what I'm saying is that so sigma of x squared, okay? The variance at level x is equal to this number. Right here. Okay? That's by a simple linear regression. Okay? He wants to come up with a formula for it. Alright? That way you don't have to have the same value repeated. You get a little bit more information from the strata that way. You don't have the same value for W repeated at each of these 3 x values. Okay? Since there is some changing in the x there, you get to account for that. So you get a column of W's which is not constant. See, these first 3 W's, they're almost all the same. 0.0000249, 0.0002407, 0.0000244, and so on. Just because of these x's being a little bit different over here. Okay? And of course I took a square root as well. So I'm taking, what is the formula here? It's the square root of C9. What is C9? Here's my W's. They were, this formula. W was 1 over the variance. Okay? So it's 1 over this formula. I put to the minus 1 power. Okay? 1 over this formula for the variance. Okay? W is 1 over the variance. I should put that equals 1 over sigma of x squared. Okay? Okay. Capital sigma, lowercase sigma, whatever. Okay. And this was the W. Okay? And these were the actual sigma squareds here. Okay? The 26 million and the 30 million and so on. Good enough? Alright, so this should be 1 over 26 million. Okay, that looks about right. Or is it right? 1 over 30 million? 10 to the minus 8? Yeah, that's right. Okay. Good enough. Now I'll go ahead and compute. I only have one regressor, right? So simply I calculate the square root of W, the square root of W times X, and Z equals the square root of W times Y. Now I'm using the notation that I used in the text before. Okay? Not in the text, in the notes. So I'm going ahead, and there's my first column of U, my second column of U, and my Z column. All right? These are the columns of the U matrix. Now I'm going to do simple linear regression. I'm going to do regression, multiple regression on these two without intercept, right? Multiple regression on those two regressors without intercept, because there's two columns of U, but there's no intercept per se. There's no column of ones, all right? Before, in the previous example, I did have a column of ones because of the very special case of the form of the variance, all right? So that was a very special case. You understand exercise 512 was a very special case, and then I had the supervisor's data going with it. Here is not the special case, this is just the generic case, all right? But I actually have a way of figuring out what W should be in this case. That's the whole point. Otherwise, you're kind of lost if you don't know what W is. All right? So I go ahead and I do the regression of Z on these two, no intercept. Okay? So intercept is no information there. All right? And so I get my beta 0, so now it really is beta 0 hat is 5974. Beta 1 hat is really this number, 7.922. All right, so Z hat is this. Okay? And then, of course, I can use that beta 0 hat and that beta 1 hat to go ahead and estimate Y as well. Okay? I just have to plug them. Why do I have Z hat? That should be actually Y hat. This should not be a Z hat. This should be a Y hat. Okay? Not a Z hat. I don't know what I did here. Because I put it in the original variables, 1 and X. Okay? But if I put in the original variables, the different variables, then I get, see, this is wrong again. Okay, this should have been 50975 times the square root of W. Okay, I should fix this on the web page, I guess. Darn it. Okay. Z hat, the output, the predicted would be square root of W and X times the square root of W. If I got the Z's in there, I got to have the square root of W's. Okay? It's different X variables. All right? Same coefficients. All right? That should be the right thing. So let's just check. It was 18.6 should be 5974 times the first number, 0.000024. So let's just check it. I'm going to go ahead and calculate. That was F8. See, this is F9 and G9, right? So let's just go ahead and use those as my thing. So let's just check. Equals, let's just check this 18.6369 as a predicted value. Equals this number times, what did I say, F9? Plus this number times G9. There it is. Okay? So that's my Z hat. All right? All right. Now, so those are those, and I go ahead and I calculate the residuals, Z hat minus Z minus Z hat. So this is Z minus Z hat. Okay? And they're pictured. Okay? Versus Z hat, here I actually have it labeled correctly. Okay? All right. Those are the residuals, and I guess they look okay. All right. Now they look a little different in the book because they've only got them plotted from 15 out to 20. Okay. All right. For the predicted value, the predicted value is between 15,000 and 20,000 for the transformed income. All right. Transformed income, which is what? What are the units of that transformed income? Those are just number of standard deviations from 0. Okay, that's your income. So, you know, you're making $8,000 or whatever. I'm sorry, this is $81,000. Okay. Did I have that one wrong? $81,000. What was the square root of a million? 26 million? Oh, okay. What was the square? Oh, that was $5,000. Okay, so $5,000 was the standard deviation. Okay. I did it wrong. I thought you were only making 8,000. It was 81,000. Sorry about that. 81,000. That makes more sense. If you're going to spend 3,000 on ads, you better make more than 8,000. Okay. 81,000, and your standard deviation was 5,000. Okay. So how many standard deviations away from 0 are you? Between 15 and 20. Okay. 5,000 times 15 is 75,000. 5,000 times 20 is 100,000. So you're between. So the actual scale of z is the number of standard deviations you are from 0. Okay. On your income. Between 15 and 20. Okay, so anyway, that's the way it came out. So, and the author changed the scale here. I couldn't do that with Excel that easily. Okay? It can be done, but I don't know. I don't want to play with it. Okay? So what else is there to do here? That was the same thing. Do I have anything else on this sheet? Ordinary least squares fit. Okay. Calculation of the weight function. Okay, so let's see. You could probably you could sort of see how good your linear fit of the variances was. Okay, and whether you want to correct that. In other words, change your weights where your weight's really correct, and so on and so forth. But I think I won't go into that. All right, I think actually one of your problems, 5.11, you are supposed to play with that. Okay. They ask you in your problem 5.11. Let's read the directions of 5.11. Let's see if we can understand what the heck they're talking about in problem 5.11. It's kind of based on this. 5.11, Schubert et al., the catapult problem, enhanced engineering modeling using experimental design, conducted an experiment with a catapult to determine the effects of the hook, arm length, and start angle and stop angle on the distance that the catapult throws the ball. They threw the ball 3 times for each setting of the factors. So there you have repeated measures. So you actually have estimates of the variance, right? And so you have, let's say, 1, 2, 3, 4, 5, 6, 7, 8 different experimental setups with coded variables x1, x2, x3, and x4. Maybe take a close-up of that information. That's the data of the problem. So here there's 3 repeated measures for each of these 4 regressor inputs. Okay? All right. So you can have your sigma squareds just like you did in this problem. Perform a thorough residual analysis of these data. Okay. So what are you going to do? How are you going to? Well, you're going to just have repeated measures. So you're going to have to see how many y's do you have? You have 24 y's, therefore. Okay, so you just have to. You're going to have to actually copy. You're going to actually enter all of this data. Okay. Some of the x's are easy to copy and paste. All right. But you're going to have 3 rows with all the same x's here: -1, -1, -1, -1. 3 rows exactly that. Then put the y's correspondingly. Okay. In the first 3 rows. So you'll have -1, -1, -1, -1, 2.80. Then you have -1, -1, -1, -1, 27.1. Then you have -1, -1, -1, -1, 26.2. Those are your first 5. Excuse me, those 5 columns, okay? And those are the first 3 rows of those 5 columns. Okay? Etc. Perform a thorough residual analysis. Study the residuals of the multiple regression with intercept. You should have an intercept in there as well. Okay? But you don't have to put that in by hand. Use the sample variances as the basis for weighted least squares estimation of the original data, not the sample means. Okay, so you're going to use, see, it says use sample variances as basis for weighted least squares. Fit an appropriate model to the sample variances. Note, you will require an appropriate transformation. In other words, a simple linear regression model is not good enough. Okay, what's the deal with that? So you need to do a regression of the sample variances with simple linear regression. Look at the residuals and study it. What's wrong with it? Okay? So he's actually saying that the estimate of the formula for the variances is not right. Maybe it's a quadratic increase in the variances. Or maybe it's some other weird thing. So you have to, it's not very much data because there's only 8 variances. So there must be something dramatic happening with the variances. They must not really be linear. Okay? I don't know, just eyeball it and see what happens. All right, just do a decent job. You can't really do a lot of work. Maybe it's a quadratic fit to the variances or something. I don't even actually know because I haven't done this problem. Okay? So you have, it says do a transformation. Use this model to develop the appropriate weights and repeat part B. So in this case, he's not going to actually, simple linear regression for the variances, to model the variances is not sufficient. But actually, I don't see why wouldn't you just use the sample variances themselves as the weights. Why even bother? Okay? With fitting that some function of x. You've got a function of x. All right? Is the variance for each particular x combination, you got 8 values for 8 different x's. Why try to force it into a formula? Okay? There's no need to force it into a formula. Okay? So you can do weighted least squares without fitting the weights at all. You understand what I'm saying? Because the x's are exactly the same now. It's -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1 in the first 3 rows. So there's no variability in the x's anyway. Just use the sample variance. That's your good function. Okay? It's a function of x. Okay? As the reciprocal weight. Okay? And then the weight, of course, is the reciprocal of that variance. So you don't need to do any kind of fit. He's just saying if you did try to fit, if you actually do try to fit it, you're going to better put it in a transformation. Otherwise, you're going to get your weights all wrong. Okay? You understand what I'm saying? I'll say what I'm saying by taking this picture off and right on the board. Here's a little fitting job. Okay, we're doing an auxiliary regression to find a function to write in the weights as is not necessary per se. Because you've simply got the why should I do that? Why should it be, it is maybe a function of x, but God knows what it is, what function it is. Okay? Why should I try to make a lower dimensional function for it? There's no rhyme or reason to do that, per se. So in other words, the W is equal to 1 over the variance, okay, of y. And I've got this negative, I've got x1, x2, x3, and x4. -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1. And then I've got my y, okay, which were 28.0, 27.1, and 26.2. Okay, these are going to give you a sample variance S sub -1, -1, -1, -1. Okay, my x is squared equal to, all right, the sample variance of those, and that's my weight at -1, -1, -1, it's my reciprocal weight at -1, -1, -1, -1. Okay, so my W, so -1, -1, -1, -1 equals 1 over S squared -1, -1, -1, -1. I don't need a formula. Okay, is a function of all 4 variables. Okay, if I did have a function of all 4 variables, remember it's going to be there's too many parameters. Okay, if you have 5 parameters, you only have 8 data points. So I think the requiring appropriate transformation is bizarre there. Okay? There's too many parameters. I don't understand what he's talking about. Fit an appropriate model to the sample variances. You'd have to throw away some variables anyway. There's too many variables and not enough data points. If you got 5 parameters, you're only going to have 2 parameters. You're only going to have 2 degrees of freedom for error even. I mean, that's kind of bizarre. So it's not necessary. So I'm modifying the problem. I'm saying forget part C.
Don't do it at all.
Try it if you want. Just see what you get for extra credit. Okay, let's make 511 part C extra credit. If you just want to play with it a little bit, see what happens. Okay? So it's curious. I mean, you just say, well, let's do this fitting problem. Let's just go ahead. I can do without the fitting. I don't need to do any fitting here. All right. It was somewhat reasonable in the previous case because the x's were not exactly repeated. All right. But here, they are exactly repeated. So I don't need them at all. Why should I do that? Okay. Only if the only value of that actually would be because these have some variability in them. These are not the actual variances. So if there were a good function for the actual formula, if there really were a simple formula for the variance of x, like it was linearly increasing with x, or something like that, all right, then you would get all the information from all these sample variances together and put into that function, and that would be valuable. But if there is no simple function, it's worthless. Okay? And so in this case, since you're trying to get a simple function where there's 5 parameters and only 8 data points, it seems a little like trying to stretch the point. But anyway, there is some value of using the S-squareds together in a formula if it's going to be a simple enough formula, which I think was reasonable in the previous example. It may not be so reasonable in this example. Okay? So have a look, though. Maybe you get it down to only 1 or 2 parameters, because only one of the x's really makes a difference in terms of how the variance does things. Okay, there's only 1 or maybe 1 or 2 variables there, so you want a subset regression model. Instead of having 4 regressors, you get it down to 1 or 2 regressors. It really only depends on that, and then put a transformation in and so on. So it might be a cute problem, this catapult problem. Okay, so I want to make that part extra credit. Yes. Well, why don't we take a break now? Okay, and then we'll go on to chapter 6. Okay?